I'm very happy to be here, and thank you very much for the introduction. And this tutorial is for the information of the subject. So, it's me on the picture, I think 3 years ago. And as Boris said, my name is Ekaterina. I normally go by Katya. If you want to connect with me on LinkedIn, it's my phone name. If you want to connect for more resources like GitHub, Stack Overflow, and I got a degree in applied mathematics and my PhD in computer science. And after that, I moved from research to industry, and I moved from Russia to Czech Republic. So it was a big change in both directions. And currently, I work as independent software consultant for big tech companies. So when they don't know what to do, they hire a consultant. It's me. And I work mostly for bank companies, insurance companies, telecoms in the area of big data development. And I think from the year 2017, I work on the project regarding big data and messaging system, and mostly with the project related to Apache Kafka. And it doesn't mean that I don't want to do something else, but the demand in industry is increasing, and there are a lot of opportunities there, and the risk is evolving. Actually, I'm more used to fixing bug productions than to presenting something. But let's give it a try. So, and as this is the database conference, and you typically look at the data at rest, but this will give you a new perspective, look at the data in motion. So it will be something different. And so the tutorial is organized as follows. It's about data mesh paradigm. So first we will talk about the data mesh. And then we'll talk about implementation challenges and implementing it with the message broker, and mostly about Apache Kafka. And we'll talk also about open operations and the search engines there. And after that, we'll do lunch. And so this is a very practical tutorial. So there will be no formulas there. And feel free to stop me at any time, just not to get lost, because it's 1 hour and a half. And after that, you will actually, as I said, it's practical, so there are no formulas. And after that, you will be supposed to run Kafka on your local machine, understand everything about it. And for the next several years, you will be like me, doing only Kafka in Apache. So this is the plan.
1 second, there is a sharing problem.
So let's go a little bit back and think about classic architecture of the application. And if you have ever seen the picture of the application architecture, it was probably like something like this. So we have the presentation layer here, we have the business logic here, and we have the database layer. And this application actually was built, and still we have a lot of systems in this architecture as a single unit. So the idea is that you build the application as a single unit and deploy it as a single unit. And this was actually the standard. And from the data perspective, it's what we have here. So we have the database as the source of truth, and the database is typically owned by the application. So the database servers, they allow you to have databases that somehow related to each other and connected. In industry, it's typically the approach to have one database per application. And the data is strongly consistent. So if we are talking about the relational database, then you have always effective constraints or things like that. And if you have the table with the current balance, and the current balance is 1,000, then you must be pretty sure that it's really not a problem. But what problems do we have here? For every change, we need to release the whole application. So once we change something, we need to release the whole system. And the deployment cycle actually is very large, And I remember the times when we needed to spend probably the whole day representing the application. If something goes wrong, you need to away, and this is a very time-consuming application. And the same technology is actually used for all the companies because we just touch single unit. If, for example, create an application in Java, you compile it, you might release, bundle, and deploy the whole application. And so it's the same technology for all the components. And individual components, they cannot scale. So if you want to scale, you need to scale the whole application. And the next step is to go from monolith to microservices. So this is actually the natural step. Just let's break the system into smaller pieces, and each of the pieces will be a microservice, and it will be deployed independently, and it will be scaled independently, and different technologies can be used. Some people think that it's an advantage to have one service written in Java and another in Python, and sometimes you have services written in Rust, and then the person who implemented the service leaves the company, and you have this beautiful service, and nobody can care about it. But anyway, this is the possibility. But actually, it also brings organizational overhead, because now you have all these small microservices, and you need to govern it. So you have several teams, they need to communicate somehow. Sometimes they're still in the industry need for code and just write emails. So it's not very easy. And actually, the infrastructure cost in general increase because you have these small pieces of software, and for each of them you need to specify how many resources it will use, so how many CPUs, how much memory, and it's actually more expensive in general than deploying this whole software as one single unit. And also, if we have this communication remotely, so the microservices, they need to communicate with each other, and this communication now becomes a remote communication. And here is when the security department comes and say, okay, you have a remote communication here, so you need to put SSL here, and the performance decreases 10%. And so actually you might have here performance issues. And we also have problems with debugging and monitoring and tracing. So we have kind of zoo of services, but if we have a pipeline which goes through several services, then sometimes it's broken somewhere and you don't know where. So we send you the data, no, you didn't, we haven't received your data, so you need somehow to identify where the problem is. And there are a lot of projects now, for example, open telemetry, but they still are in their infancy, so they are not widely used, and not all the technologies can use them. So we have cells in Python, we use one framework, and Java another framework. But what do we have from the data perspective here? From the data perspective here, each service has its own database. So customers, they can only with times and payments. And the API encapsulates business logic, and the data is not visible outside. So before we had one single application, and the data wasn't visible outside, so it can be somehow implemented there. And now we have a small piece of data, and the data is not visible outside again. And it's not actually ready for bulk access, because typically the communication interface is some kind of REST API, so we get from HTTP. And though these services, they have their database, but if you see your customers and accounts, you may understand they are related somehow. So if we have account, we need to understand which customer the data is. This is how it works. Actually, I can say that this is the standard now, still with a lot of challenges, and why it couldn't be done in the right way from the very beginning. Because currently we have these containerization technologies, virtualization, you do just Docker image, you can deploy it everywhere, and this is automatic. So it's very easy to have the new release of the service.
Can we ask a question?
Sure.
So what is the problem with the 7 bullet from the data perspective, that the data is not from outside? Is that a desirable property, or is this actually from security or privacy perspective needs a class. I don't understand that second bullet as a concern.
It's not a problem, we started from the relational model when we have the entity relations between them and the broker, for example, like in customer and accounts, but they are still connected. So we need still to integrate them somehow. And it's not clear how to do because we have currently customers in one database and accounts in another.
Okay, so what you're saying basically is on the right-hand side, these are independent databases.
Yes.
And so there's no integrity constraint across them. So
Yes.
it's a standard file system problem that you have multiple files,
Yes.
you want to keep them consistent. Okay, now I get it. Thank you.
This is the traditional data silo problem of, decades.
No, I understood, but the way that I interpret it is slightly different, so just a clarification. Thank you. So,
But this was actually operational way, and I don't like this word very much, but we were talking about the business process or workflow, so something that happens because of the business requirements. And here we have operational way, so here we have data analysis, and here we need to run analytical queries. So, and typically, this data analysis is performed by another team, so just another people sitting somewhere else. And they extract the data from various data sources and put this data into the repository somehow. There may be staging areas, performing kind of transformations with local data analysis, creating data analytical model. And this is actually the approach which is optimized for analytical workflows. Apache Hadoop was a standard for a very long time. Now we are switching them off one by one, and the company they migrate to Azure Data Lake. But anyway, it's actually the same thing, so honest. And what are the problems here? So the central data team becomes a problem. So now they extract the data from every different sources and they need to understand them. And frankly speaking, I don't know how they do it because now they have everything without the excellent domain knowledge of each of them. So it's not clear how to understand domain data. And you also have data quality problem because you had a relational database with all these constraints defined, and then you put it somehow into the data lake and use a lot of information, some various memories, some functionality balances about it, and actually you have less and you know how to do that. And probably something which forces us to move to some different paradigm is the need for real-time analytics. So currently the business demand is to analyze the data in real time. For example, if you have fraudulent transaction, you need to understand the transaction is fraudulent just right away, otherwise it will be just too late. And this is a classic use case, but now we are forced to move a lot of analytical operations just to real-time frame. So the idea here is very simple. We were talking about microservices, and let's bring the same concept here. So let's just put the microservices into the data hub, and here we will have domains somehow connected, and the definition and access of the data is decentralized, so we don't have a big data lake across everything now, and we need to define data context. So actually the data, and what is the data? It's a table, it's a file, it's a kind of schema, also what it is. And the data we should govern where it is created. So the team which is responsible for the accounts, they know the best everything about the accounts. So this is actually their responsibility. And all the changes, all the requirements should go through them, and they should expose their data product in the best way. And another thing is that data products, they are must be published and available everywhere. So if you're talking about data products, in services, we have this Swagger, so we can generate API somehow there, but we need something also here, because the teams in large organization, they need to understand actually what they already have. How do they get this information? So it's not clear. We need the tools which support this value. And so here probably it looks like, in Czech language we say "Spadky na stromy," meaning back to the trees. So meaning that we are returning to the very ancient times, because we were fighting for a very long time to encapsulate data, to put the data inside the service and make only the service visible. So it's the service, invoke the service, it's the content, and don't care what's inside. And here it's actually going back, because here we are exposing the data. And it also it brings actually some benefits, but it also brings up some changes, and we discuss how to do it. So here comes the data mesh principles, and there are 4 main principles. They were described by Jean-Marc Bloch. This is actually the paradigm of data mesh paradigm, and they are written here. So first, domain ownership. Data is decomposed by the business, no big data lakes anymore. And data is a product. So domain data, it must be shared as a product. It must be on the product quality. So you cannot just expose notional table. There must be some kind of rules what is actually inside. So what's how you can make this data available to other teams. And there must be self-service data platform. So we need the possibility to manage the data product for all users. And here you may say, okay, but this is the very technical thing. So you need the self-service data platform. So just implement it. There was a problem here, but the problem actually that nobody has implemented so far. So if you have a kind of some students who doesn't know what to do, so this is the possibility. And we also need data governance here. And so what do I mean by that? We are talking about the autonomy. So each team, they are responsible for their data, they expose the data product, so they select the technology and so on. But there are some rules which must be held across the organization. So for example, some of the rules, they come by law, for example, GDPR. So we need the possibility to remove the client data by law. So nothing to invent here. And some of the rules, they come from the security department, for example, security of the communications, and some rules, they come by law again. So, for example, if you have fintech problem, for example, a bank, you are required to have more than one data center in different locations. So, even we have the autonomy for the teams, we still need to have the kind of rules. Every service must deliver them. And these principles, they are technologically agnostic. So we are not talking about the implementation at all. So here we have the rules, we must follow them somehow, but it's not about the technology. What are implementation challenges here? And the main challenge is actually how the data flows between business domains. So exchange cross-service API is not enough, first because it's not ready for bulk access, and second is that if we expose the data, we don't have the time to create all these services manually, somehow discussing them with all the teams. So let's invent somehow some other contract. And we also have the problem about data consistency, synchronization across different domains, and develop the classical database. And to make everything work, as we have a lot of small data pieces here, we need to integrate it well with a large range of tools and platforms. And here comes the idea. So if we take all these principles and implement them with the help of even Broker. So let's talk about implementing data mesh with strings and even in kind of occurrence of something. So if something happens, the system might publish the event, and events are immutable. So if something happens, it cannot be unhappen. So if you said something you were not supposed to say, it's already done. And they are timestamped, so they have the time. And it's actually a very difficult question, where the time comes. So is it a business time, or is it the time when the event was related to the system? Probably it's the time where we start processing the event. But let's not go deep into that. And events are durable and repairable, so we need this event to be persistent, just to be able to reproduce the event and restore the state. And we also need all this implementation to be high available and fault tolerance. And it's not about the data mesh, but it's actually the general requirement for all information systems now. And so here we will be talking about event producers, event channels, and event consumers, and how to implement all these data mesh principles for these events. And let's put it a little bit aside, and let's talk a little bit about message brokers. And in this presentation, I will concentrate mostly on Apache Kafka, though if you have some questions, how to access modern message brokers. So Kafka is a messaging system, and it means that producers and consumers, the participants who want to communicate, they communicate asynchronously, and they communicate through an intermediate destination, and this destination is called message broker. In our case, it will be Apache Kafka. And producers, they send the message to the message broker. Consumers, they need the data from brokers, so they need to express the interest in receiving such messages. And everything is distributed, so we don't care if it's in one computer or in some kind of context or cloud environment, several computers. So this is absolutely transparent. But these things can be said about any kind of message system. So what makes actually Kafka to be Kafka? And there are several features here. First, it's a cluster. So the cluster architecture is naturally built in Kafka, and when you install Kafka cluster, you're supposed to have several brokers, though of course you can have one on your laptop. But in production, we will have several brokers, and it's replication. So the data is replicated when we send the message to one broker, it's replicated to other brokers, so we don't afraid to lose the data. And another feature is rewinding. So if consumer reads the data is not deleted from Kafka server, so it's still there. And if consumer, for example, loses the data to hardware server or to software server, it can connect to broker again, and if the data is still available here, it will read the data again. And the data is kept on the broker for a certain amount of time. By default, it's 7 days. So, but plenty of time to connect again and read the data again. And you can, and this period is called retention period. And you can also specify retention by size. So, for example, you may have the last 1 gigabyte of data. Though I personally don't recommend this approach because you cannot predict this size. So, for example, one marketing department, they produced the servers who started to send a lot of data because of success, and the consumers, they cannot read the data, so the data is deleted automatically. And so it can be a problem here. So these 3 features, they are actually typical characteristics of Apache cluster. The main concept of Kafka is product, and you might think about topic as a destination. So you send the data somewhere, you send the data to the topic. If you're familiar with any kind of message system, like you, GMS, whatever, they have a concept of topic of you. And messages are grouped into the topic, and each topic has a name. So this is how we identify the topic. And the good pattern is that the topic groups messages of the same type. So if you have payments, it goes to the topic of payments. If you have customer events, it goes to the topic of customer events. And it's a publish subscribe pattern. So producers, they send the data, and they don't care if somebody reads the data or not. So they just send the data and it's over. And consumers, they read the data, Typically, products has several consumers and they will independent. So producer just says that something happens and all the consumers receive the notification. And don't forget about the retention, so the data is persistent. So there is nothing like Kafka in memory, the data is stored on disk. And they will be removed after retention period. Attention period can be specified by topic, so 7 days, 1 day, whatever. And the data will be removed even if the consumer has been time written, so they will be removed automatically.
Sorry, Ekaterina, just a question. Maybe I missed it, but what is the exact difference between messages and events?
There is no difference here. So when we're talking events, kind of philosophical concept, and messaging is something, message for record is somehow intermediate and I will go.
Class, child class.
Yeah.
Message is a event.
It is supposed to bring implementation inside the domains or to communicate in the domains?
This is a very good question. And actually, the Kafka clusters, they expand extensive compute and they are typically multi-tenant. So though there are some other problems, but typically we have one Kafka cluster in the whole organization. And sometimes we have several ones, but it's not because of kind of responsibilities concept. But if you have low aggregation, latency is not a requirement there. So we will have some problem not written at all. And so for kind of for use cases, kind of aggregation, we do the cluster with chip disks. And for financial transactions, where the latency is important, we do cluster with a high level disks with high speed. So technical requirements. And so what's the topic inside the topic? We have partitions. Topic is broken down the partitions, and partition is actually a unit of scalability. And partitions, they have index starting from 0, and the message goes exactly to one partition. And this is the producer who decides where to send the message. So producers actually says that I'm going to send the message to the partition number 0. And we will talk about the strategies, how to send the partitions. And the data is sent in event-only fashion. So the data is mutable, and you append the data into the end, and it receives the asset which actually the position inside of the topic. So here we have another feature that when the message is sent to the topic, we don't have the total ordering. And actually we lose total ordering here. Because if we are sending payments, the payments they will be not related to each other. But if we are sending updates of the customers, then it's actually we need to receive the updates of the customer in the proper order. So here it's important, and we can guarantee that the data will be in let's say that the data will be inside one partition. It will be ordered. I just realized that I have all the virtual slides, but never mind. I will overcome it. So inside one partition, we have ordering of the messages, and we don't have total ordering.
Can I have one question?
Yes.
So on the channel between the producer and the buffer, there might not be that one message arrives earlier than even if they arrive at the same partition.
If you have several producers, then they are not synchronized somehow, of course. So actually, they send the message, and it may arrive in any order into partition.
But from the same producer.
Well, from the same producer. Producer actually creates the batch of the messages, and I will talk about it later. And the messages will arrive to the partition in the order in which producer sent them.
So the network will not let's say miss them on the level. So nothing really proposed.
No. In one partition you have the ordering, but you don't have the ordering across total.
Sorry, a quick question. So there's nothing that prevents the data producer to be as well as data consumer, right?
It can be one microservice, why not? Yes, sure.
I was thinking like for data analysis, you consume data and then most probably you are going to publish the outcome of the data, whatever data analysis you are doing. So you are also producing.
Yes, and this is actually the big class of applications, and we'll talk about it later. So typically, the streaming application, it reads the data, processes the data, and produces the result right into Kafka. Yes. So it actually serves as kind of enterprise service bus.
There's one thing. Is there any kind of elasticity in the partitions or dynamicity, let's say? So can I remove a partition?
This is a very good question. Yes, you can remove. And this is the only one thing which is allowed to do. So you cannot add. And this is, you cannot add partitions. Yes. Once you create the topic, it has a fixed number of partitions, and you cannot add them. So no, it's not elastic.
But you can remove.
Yes.
And what happens with the data? Is it lost?
It just removes. But yes, it's lost
So
basically.
the data is lost. So I mean,
Yes,
I can remove them.
It's not a very typical situation that we remove the partitions, but sometimes probably you want to descale your topic, so you don't have enough of data, and you decide just to have a small number of partitions, and in this case you can remove.
But then the data is lost.
Yes.
So it's not reallocated in the partition.
No, but you might have of course manual migration process, so it's possible to run kind of scripts. They are available. But basically, this is the unit of scalability, and this is where your scalability ends by the number of partitions. So you cannot scale much on the client. So we have the cluster, and we have when we create the topic, we need to specify the name, and we need to specify a replication factor. And the replication factor means how many topics we are going to have. How many copies of the partitions we are going to have. And if you specify replication factor as 3, it means for every partition we are going to have 3 copies. And one of these copies is needed, and the others, they are followers. So here the data is needed, and the rest are followers. And producer actually, when the producer sends the message, it sends the message to the leader. And after that, the message is replicated to the followers. So here we have leader for partition 0, and for partition 1, and partition 2, and partition 3. So producer first needs to know where the leader is for this partition. So it sends a partition, and it needs to know where the leader is, and then it sends the data into the partition, and after the partition is replicated. So if, for example, one broker goes down, we still have the copies, and another leader will be elected for all the leaders which are presented for all the leaders from the broker. And there is also a concept about the replicas. They must be synchronized, and technically it's a little bit complex, but basically synchronized, it means that they are not behind the leader. And by default, the lag is 30 seconds. So for 30 seconds, they should not have any lag, so they choose. And regarding the message, so we have the message, and the messages, they have key in the key of when you have now. And keys are not unique, so keys are not like keys in the database, and keys are used for partitioning. And to ensure that the data with the same key comes to the same partition, we might take the hash of the key and then divide by the number of partitions, and eventually the remainder is the number of the partition. So basically, this is the default strategy of the consumer. So if we have updates for the customer records and the natural ID here, the natural key will be customer identifier, and for all the customers with the same ID, we will get here the order of the updates. And it's just a byte array. So producer serialize the data into bytes and sends bytes there, and consumer then receives the data in bytes and serialize them. And Kafka broker does not know anything about the message selection. So Kafka broker cannot look inside the message and perform some kind of logic over this message. So it's kind of byte in, byte out. And I don't want to say garbage in, garbage out because it's not garbage, it's the real data. But this is actually why Kafka is so fast. Broker does not know what's inside. Just receive the messages and send the message, and that's basically all. And it also include headers, so kind of key value pairs for metadata, for example, encryption parameters, probably the types of the data, so sometimes just information which does not fit into the message. And just not to make the impression, it's very simple. This is actually the minimum deployment feature of the Kafka cluster. So we have brokers here, they communicate with each other because of the data application, and we have producers and consumers, their client applications. So all of these errors, they are actually network communications. And we also have Zookeeper cluster, and when I'm talking about kind of server, I typically talking about the cluster, so there are several instances there. And brokers, they need to they send the updates to Zookeeper, just saying, hey, I'm alive. And by that, Zookeeper understands that the broker is alive, and otherwise it just kicks the broker out of the cluster and performs this election process, so considers the broker to be failed, and all the leaders for the partitions will be realized. And those of you who probably know about Kafka more can tell now that Zookeeper goes away from this ecosystem. In the new release, we will not have Zookeeper. And by the way, Zookeeper also starts the metadata there. So currently, this is the source of truth for the whole cluster. But it will be removed in the future versions of Kafka, but it does not make this picture simpler because all these functions of the Zookeeper will be taken by Kafka brokers, and you will have the brokers of different roles, so brokers and controllers, and basically the picture will remain the same as here. The types of brokers instead of Zookeepers. So how to send the data? We need to create application which sends the data in Kafka protocol, and this is TCP level protocol. So not kind of TCP, so it's custom protocol. And a lot of languages are supported, a lot of frameworks are supported. So it started with Java, but currently we can use Python, .NET, Kotlin, whatever you want. So Kafka is very widely represented everywhere. And to send the data, we need to select the strategy, and the default strategy is to send the data with the same keys to the same partition. And other strategies can exist. For example, round robin, we don't have keys, so we just send the batches to one first partition, to the second, to the third, and do that again. And for example, in Netflix company, this is the default strategy because it's very fast. And then they can be also explicit strategy, so you just say to which partition you send the data, or custom, even you can implement your own custom on the client side. And a producer interacts the data to the reader, so the first question is, who is the reader of my partition? And this is metadata, and metadata is cached, so no kind of performance overhead here. And it also needs to understand whether the data was sent successfully, so it waits for the acknowledge. And there are different strategies for the acknowledges. For example, the biggest strategy is just the data came from network, probably it wasn't sent from the broker. And the strongest strategy is that we receive acknowledge from the leader. So the data was sent to the leader, and the leader just saves the data and sends the acknowledge. And the strongest strategy is that we receive acknowledge after data replication. So we send it to the leader, the data is replicated to the forwards, and then acknowledge was sent to the client. So basically, these are three ways how you can define if you don't want to lose the data. And this picture is basically the life cycle of the producer. So we need to choose the partition, serialize the data, and create batch per topic and partition. So the data is always sent in batches. So we don't send the messages one by one, just to be a high performance system. And we will also compress the messages and so on. And so we select the partition, we serialize the data, and create the batch, send the batch to the broker, and then probably we will receive the acknowledge or will not receive the acknowledge if the failure happens. And then you can reply. And the good news here is that you don't need to program it. So this is something which is done. So which is this is the default Kafka framework. And please don't try to improve it very much because it's already tested. And I have seen several times that people just want to glue messages together, put them in batches by their own, and it's not very easy thing to do. So just trust the system. But what you have here, you have a lot of configuration options. So you can configure all these things, the size of the batch, and how long should we wait for new messages. Probably the batch is not ready yet, so should we wait? Or how long should we wait? And this is another configuration parameter, and the number of retries and the delivery timeout. So when we run of delivery retries and when we run out of so when the out timeout expires, we either send message or it will be a failure. So going back to data mesh, so here about data ownership, who is in charge of the data, and in charge of the data is data owner in Kafka ecosystem. This is the producer. So producer is responsible to send notification about the data, and producer is actually the data is produced in the microservices that understands the data, and we need to define entities and boundary contexts and regex. But basically, all these things they are produced in responsibility.
Could you please tell us a little bit more about how you expose the data? I mean,
I will
okay.
in 5 minutes.
Okay.
Okay, sorry, let me ask a couple of things more about. So I'm not sure. Maybe you mentioned and I missed. Is the data deleted or purged from the topic, or does it just grow and grow and grow forever?
It's deleted automatically after the retention period. Okay. So the data which is older than 7 days by default will be deleted.
Okay. So except for this, let's say for this little detail, which is the difference with HDFS? Because the protocol you mentioned now is kind of similar, no? In HDFS, instead of having this pack or this batch, you have a chunk, and then you wait until you have the chunk, and then you write the chunk.
The main difference actually is the messaging system. So the main use case is messaging. It's a data pattern. It's a data integration pattern. So you send the data, you receive the data. After that, the data could be probably deleted, but it's not. So and it's deleted while the system thinks nobody cares about the data. So it's more like, for example, GMS, RabbitMQ, and sort of like that.
Hello.
Yes.
Exactly. The difference in the ASD is that in one case you have permanently the data, and in the other you have none.
But there is a case about storing the data with the context. So how to read the data? Always full. It's not a push system. So the consumer asks for data, and then you data for me. And it's actually the same picture, but somehow mirror. So the data is collected in batches again, and the data is sent from the broker to the consumer in batches. And again, you can configure so how the size of the batch and how long to wait for new messages and things like that. There are a lot of configuration options there. And regarding the consumer rights, so actually we are talking about consumers, but the unit is actually a consumer group. And consumer group, you might think about it as an application, so it has kind of group ID property and it identifies the consumer. So when you might have, for example, payments applications and mortgages applications, and they receive the events about the customer, and every of this system has its own consumer group ID, and it receives all the data. So they just receive all the updates. Inside consumer group, you have different consumers, so different, you might think about it as threads. So, and each partition is assigned only to one consumer in a consumer group. And of course, if you have less consumers, then more partitions can be assigned to the consumer. But actually, here you might see that these partitions, they are actually the unit of parallelism. So the maximum parallelism you can reach is the number of partitions on the client side. So if you have no consumers inside consumer group, then they will do nothing. No partitions will be assigned. So this is how this actually happens here. And if consumer leaves the group or joins the group, a rebalance happens, so the broker understands it because consumers will not send habits, and the partitions will be removed from the consumers in the group and will be assigned again to all the consumers which are considered to be alive. And when the consumer actually asks for the data, so the consumer asks, do you have new data for me? Do you have new data for me? And what it means, new data. And here, the concept of the offset comes again. So the offset is an generator, and it's assigned to the message by the broker on message receiver. And if you know consumer group, partition, and offset, you actually know which data is generated by the consumer group. And this is incrementally growing function, so it's growing, but it might have gaps. But the idea from the client here is that consumer commits offsets. So it says, okay, I have read this data, I have processed this data, and there are all different strategies there. So the data may be committed automatically in the background thread. I don't know why they did this, why they put this option. And the more usable strategy is when the consumer comes to the explicitly, so it processes the data and says, okay, please claim this data, I have already processed this data. And offsets are stored in Kafka by default, though they might be stored somewhere else, but by default you have a special method as offsets.
And that means there's no update, no update is possible.
Yes, you cannot. So here's actually consumer behavior here. So you cannot access the message by behavior. You cannot delete something in a behavior. You cannot update something. So these are truly immutable messages. So these are truly immutable. You write the data there and you cannot update them. But there is actually a way to access the message in the middle. So and we have two indices there, and first it's offset index. So if for some reason you know the position, you may put your consumer to the special position. So you can say, okay, please read this topic, this partition from this offset. And there is also time index. So you might put your consumer to the position with the earliest timestamp which you specify. So for example, please take the position for the first message of this day, something like that. But no index by the content. So nothing like in database here. And actually, so just making a recap, we have producers and consumers which are decoupled, and we have a Kafka cluster with brokers and Zookeeper and brokers, they do processing of the messages, and Zookeeper stores the information and another information. And the contracts, they are defined on the client side. So broker doesn't know anything about the messages at all. So the contracts are responsibility of the producers and consumers. And going back to the question and going back to the data mesh principle, so here we have the data as a product, and data is actually a first class citizen, and we need to expose the data as a product. But how do we do it? If consumers and producers, they need to agree somehow, so how to define actually the contract, and we can do nothing on the broker side because broker doesn't care about it. And we had already with these events immutable attached and product, but now we can also move forward and use a kind of self-describing semantics and syntax, so how to actually describe the data. And here we have another participant in this ecosystem, and it's called schema registry. So in real life, the data is spent, and producer and consumer they need to know about data types, and data types are evolving. And the standard which is used, actually somehow, currently most standards are supported, but the most common standard for defining data types in Kafka is AVR. So the idea of AVR is the data comes with the schema. So you have schema as a part of the message, and you have data as a part of the message. And in AVR, you define this context something like that. So you have these data specified in JSON, and this is actually technology agnostics. So it's not related to Java or Python or something like that. So this is actually the contract. And you may guess that here we have namespace, which is somehow something like package in Java, and you have the name of the entity, and you have fields, so these are attributes, and somehow this maps naturally to the object in programming language. And you can also put constraints, like for example, null constraints and default values and so on. But actually we define our schema. And the schema is stored externally, so the idea here is, okay, let's send the data together with the schema, but the schemas, they don't change often. So let's save somehow some space and some time, and let's put this schema separately into schema registry and just send the ID. And this is how it's implemented. So the producer must know that it will use AVR as a serializer. And the first time it sends the data, first it checks if there is such schema in schema registry, and if not, it just puts the schema into schema registry and sends the ID of the schema together with the message. On the consumer side, consumer again, it needs to know that it will the AVR format will be pushed as the data format, and it will contact the schema registry. So looking at the ID of the schema which comes with the message, get the schema and deserialize the data to the object. And so it's kind of one more communication with another server. And again, if I'm talking about server, it's a cluster of schema registers and so on. So we actually complicating our deployment. But schema can be cached on the client side because schemas are immutable. So you don't need to go to schema registry very often. And in terms of implementation, it's actually a Jetty server. So this communication is done through the HTTP protocol. But again, the schema is checked on the client side. So actually, you can ignore it and send kind of garbage to Kafka and break the system. So it's again the responsibility of the producer and consumer to use proper serializers and so on. And when I'm talking about the schema, so actually, again, some concepts are mixed here. Every time we update the schema, the new version is created. So we may think about schema as a subject, for example, customer data, and new business requirements comes, and we need to add some attributes probably, and we create a new version of the same schema. So subject is actually the concept of the schema, which is evolved inside schema registry. And but anyway, every time you register the new schema, you get the new schema ID, you get the new version, and you may check also compatibility rules. And I will talk about it on the next slide.
No, sorry, the subject is something like producer, consumer, something like this.
It's something like customer payment invoice, So subject
The
is
name of the table equivalently, I mean, if you think in relational terms, it is something like what the name of the table would be.
yes.
Okay.
And yeah,
Application. Yeah, so the similarity is replicated as well.
yes. And actually, it's replicated, but it doesn't have its own storage because schemas are stored in Kafka by default. I didn't want to go into much implementation details, but you have the topic inside Kafka. It's called underline schemas. And the schemas are stored there. So it's naturally replicated because it's inside Kafka topic.
What happens if there's a new customer consumer of data? We should the newcomer should follow the already established contract, or we can create a new version of it?
Yes. Imagine that the data changes and we create a new version of the consumer. And it depends if your consumer is interested in these changes. So, and this is actually about this topic of compatibility. So it depends what you upgrade first. And by default, this is backward compatibility. So by default, you upgrade the consumers first, and it means that the new consumer, they must read the old data. So you can do much here, so you can delete fields, and then you can build these fields and optional fields, so that new version will just fill with optional values. But this is default. So you upgrade consumers first, and the new version of consumers, they are supposed to understand the old data. And another compatibility approach is forward compatibility. It's actually from the other side. So here you update producer first, and new version of producers, they start to send the data, and the old version of consumers is supposed to read the new data. So here are rules I did fields, and the old version of the example we just ignore this. And it's probably a little bit complicated just to catch it now. But there is a big table in the Kafka documentation. So what you can do and what you are not allowed to do. And I must say that this is actually the most painful thing here. Because of course you can have changes which are just not edit and remove fields. So attribute changes and what to do, and migration processes and evaluation rules, so how to do it. And if you are in between of new research topic, please do something here, because we struggle with this problem a lot. And another thing is it's not implemented very well, so actually there is a big room for improvement.
Excuse me. When you create a new consumer and it is supposed to read all data, but how many generations of schema back is supposed to read?
It's also a property on this schema registry content. So basically in Kafka you have either one schema back or transitive, all the schemas. And here we are coming to another topic. So here we can also talk about storing state. So far we're talking about the events. So something happens and we send the event. And all the events, they are written into the topic. Imagine that you send the updates about the customer data and the keys the customer ID. So you have this chain of the updates, and probably consumer is not interested in all the changes. So probably it's interested only in the last change. And we can somehow skip updates in the middle, so saving time and space and so on. So this is actually another case. And we use Kafka for storing data. And this is when we create the topic, we need to specify if this is delete from cleanup policy. So it was if this is something we're talking about, so it deletes everything after retention, or it's compact. And in compact, it's storing state and it deletes about everything but the last key. So for each key, Kafka guarantees just to store the latest value. And in case of of updates. If you send the whole data about the customer, it will be just the latest update. So actually, the latest snapshot of the data. So this is actually how you can think about it in both ways. So we have stream, and this is account transactions. So we perform movements on the account, and this is somehow maps to the table. And you may imagine the service we just stores the balance for the account. And in this case, the service will just send the updates for the balance. And if you just show the data to the customer kind of dashboard, then you just need to show the latest balance. So this is another way how to represent the data. And probably it looks like and sounds like cheating because I told that there is no deletion in between the tokens. So if you read the data stays there, and that's actually true. But for compaction topics, there is a special process, and that's why it actually calls compaction of the token. And for each partition, it's not partition, segment one, it doesn't matter here. So there is a special process which actually creates the new version of the data, just removing the old values for each key. And for each key here, we have only the latest value. And there are certain rules here. So, for example, key is mandatory, and Kafka guarantees to retain the last records. And here you may also delete the message. So if you send the value as null, the message just will not be present in the version. So here it's actually one of the most common questions: how do you do with GDPR? Because the data is not removed here. So here you can remove the data. And so here probably comes the question, which is very popular in Greek literature. So is it a good idea to use Kafka as a database? And the answer is no. Because you should remember here that we can use Kafka as a source of truth. So you can store the data there in compacted token. And when Microsoft starts, it can just read the data and feed its own database or storing the data in memory. But the source of truth is considered to be Kafka. But the access to the data is still sequential. So if you need to have the data on the client side, you need to read all of it. So there is kind of no way to escape. And so you cannot access data randomly, no kind of access by index. I mean, the various messages are not indexed, and there are no transactions. So no like place with transactions, so nothing of that you don't have in Kafka. So basically, you can use it as a peak value storage without a good way of access, but actually you cannot use it as a database.
If you cannot ask queries, it is called a data graveyard. Yeah, for all the students here, the purpose of the database is to answer queries. If you cannot answer queries, this is basically a log file. Right, pretty much the equivalent is the log file. The SMIL somehow is the log file, not the database.
Yes, yes. I'm actually mostly referring to the Greek literature. So if you Google something like, can you use Kafka as a database, you will find a lot of blogs and articles there. So here, answering this question in advance. But you can have different types of ways here. And here we are coming to the streaming and data transformation topic. So the consumer receives the data, but typically the consumer does not want the data in the same format which it was sent to Kafka. So it means somehow to convert it into its own model, to perform kind of transformations, probably aggregations, and so on. And the transformation can be done on the consumer side, but it can be also done somewhere in between. So these transformed results, they must be, they may be available, so they may be of any use for other clients. And in this case, you may have a service somewhere between input topic and output topic, and you just process the data and produce the results in a streaming fashion. And the big number of use cases here is to use streaming for enable real-time analytics and for notifications. So, for example, security department, they always come with the requirements just to separate certain HTTP requests with certain URLs, just put them into a separate topic in real time. And after that, they analyze it somehow. I don't know how. Nobody knows. It's a big secret. But anyway, they can come with a certain rules. So how to extract some data from the system to put it somewhere else and to be available for some kind of analysis. And further transaction is another good example. Another example. So, for example, in Czech Republic, we still pay in Czech crowns. So if when we go to a vacation by car, we always stop at the latest petrol station to refill the car to pay Czech crowns without all this conversion. You even have the sign there. This is the latest stop in Czech Republic. And when you pay, you receive the SMS because they got your transaction. So they send you the SMS. Okay, you are leaving the country. You do buy travel insurance. Probably it's the time to buy travel insurance. Please click here. So there is no way to escape, and there are a lot of things. Yes,
Yeah.
I managed.
One question, please. There's something I don't get. When you describe the database, you said that the databases are responsible for the data, and then at some point we need to have federated governance, right? For instance, in order to, I guess, reconcile data if they are inconsistent. How does that fit the picture here? Because would that data reconciliator be a kind of data consumer that's also sorry, I'm
If you can perform some kind of checks for the policy of data in real time, and sometimes of course it's broken because the user sends kind of garbage there, and you need the process to somehow to repair the data, and it's not done somehow automatically, so it's still a custom process. Every company implements it on their own, and it's again a bit some of the research. And regarding the transformations, so you may have a different kind of transformation status. So just take the message, transform it to some other message. You may have a filtering there. So it's actually just drop some messages. You may have aggregations. So for example, let's count for each element, let's count how many elements of each color do we have. And every time we produce the result. So this is kind of query which runs continuously. So the elements, they are arriving into our system, we calculate them, we receive the new count value, we produce the result. So this is actually the way how to query the table. And we also may divide the stream into windows, and windows, they can be count-based and they can be time-based. So just not to calculate the aggregates with the whole stream, but calculate the aggregate just on part of stream, and every time the window closes, you produce the new update. And so, and this is actually the big picture of streaming. So you have input data, which comes into your application, you have output data, and you have local state. And this local state is typically in memory database. By default, by the way, it's RDB, although you can put somewhere else. And you also have kind of periodic checkpoints because we still have these availability requirements. So you put the data into remote storage, and this remote storage can be Kafka. So this is actually, you read the data from Kafka, you produce the data to Kafka, you process the data somehow in between, store the data in memory, but the state is backed up into Kafka. And this is how these applications, they are implemented. And different frameworks like Apache Flink, Apache Spark, Kafka Streams, which are the most close framework to Kafka ecosystem, was created by the same company, and Apache Beam, which allows you to write the abstract queries there. So this framework, they are supposed to be used for implementing such kind of applications. And you may ask here, and what's actually the difference between just having producer and consumer? So I can just consume the data and process and then produce the results. So what's the difference by using special framework? And the answer is that they provide you certain functions for the joinings and accounting, and they also provide exactly once guarantee. So if you process the element, you process it only once. Even if something fails, even if something, if you get a new instance of the application, so this is actually done transparently. And so it's actually in Kafka stream, so you need to have application, and it works as Kafka client. So they have several instances of applications working in the Kubernetes, and they act as the consumer, so they actually receive a kind of portion of the partition. And this is kind of, as again, these streaming applications, they are scalable as much as the topic is scalable. So actually, the maximum parameter here is the number of the partitions. And a lot of different questions here, but actually, this is the architecture. So if you were listening to the keynote from Monday, so in this keynote, the data graphs for processing were created, and these data graphs are created here by the framework automatically. But here you must be aware that if you, for example, need to join payment and order, the payment and order to be joined, they need to come to the same instance of the application. And this forces us to have a kind of requirements, and this called like a partitioning requirements. And basically, if you want to join something or process, aggregate something, process something together, then the number of partitions must be the same, and the elements which are supposed to be aggregated must come to the partition with the same place. So, for example, and the easiest way how to do it is to do it by key. So, the key strategy is still that you have the control over it. And so here, if this is silent to the task, it never changes. So if it fails, together with the local state, it fails completely, and it will be created somewhere again on another instance with the same partition assignment. And actually, I was thinking about aggregations. So the question here is, and I was thinking also about Java, so it's implemented Java. Java is not trendy anymore. So here probably we may have the question, can we do it without code? So can we do it just somehow declaratively? And the answer is yes. And for this, you will need another server, so another cluster of servers. And these are called KS12. It's not Sigma, but it's here as well. Somehow we call it like this. So KS12. And this syntax is something like you should be familiar with. But so you need to specify where to read the data, the format of the data, and the data must be structured here. So nothing like just bytes. So we assume that they will have a format like JSON or AVA, something like that. And you also have another dimension here, as we are talking about strings. Then we also have time dimension, so you can specify windows and so we can calculate aggregates over the whole strings or just part. And I have heard several times here that everything in query optimization has done already. So this another type of queries you have here, and you also have kind of technology restrictions. So another research topic. And it's probably the picture of how it looks like in the deployment. So basically, you have this store server, and the queries they run there continuously as applications. And you can communicate with the server through REST API, sending queries there. For example, you open the console, you create the query here, it starts working, reading the data from Kafka, processing and producing them back. And you may also bundle your application together with query file, and so just your application will consist of the server and the query file. So no problem here again, but it's just very easy to create such kind of application here. But no magic inside. So if you have this server, then it means that inside it will generate the normal Java application with Streams framework and having local state with RobustDB and having backup in Kafka. So basically everything we have talked about already. So regarding data mesh again, we were talking about data products and data domain, but self-service data platform we don't have yet. So we need to implement somehow for message brokers. So we need to monitor publish data products, discover products. We need the ability to ask for product change and support some kind of policy automation. And what do we do currently? We just store everything in Git. Everybody who needs to perform kind of request, we just create a merge request, so it's a very low level. We need something more high level. And and this is open topic now. And we also, regarding federal governance, there are a lot of requirements because we have restrictions by law, by security department, whatever, but still we don't have any tool for federal governance. So we cannot introduce the rule to the whole class. It's still very low level. And we need to have possibility to move one level back, one level up. And we have many research challenges here. So this is a very new paradigm and principles and practices of data mesh. We don't have them yet, so we don't know which will work, which will not work, which is good, which is bad. And we need to design effective governance models. And as I said, this is the most painful question here. So how to create data governance. And we also need to understand if our data mesh is of high quality, so how to measure it, so how to have kind of metrics here, and the data quality checks. And as we constantly probing the data, which was consistent somehow into messages, and we lose this consistency, and we don't have transactions, and you cannot have transactions in Kafka because there is no transaction manager, so we cannot have any kind of distributed transaction. And we need to understand how to live with this eventually consistent data. So the data will be consistent. So we don't know when, but somehow it will be consistent. So this is another topic. And as it's still the cost of infrastructure is not high here compared probably to the standards we should have before, but still we need to have operational cost optimization. Because, for example, you have class with a certain configuration, and what's the optimal configuration? You have a lot of properties you can configure on the class, like batch size, how long to wait for new messages, and so on. The batch size on the consumer, the number of threads, a lot of properties, and typically they are with default values, so nobody knows how to create this configuration in an optimal way. And this is again here, and probably it will be the subject of research. I will do it in the near future because I need to solve this problem somehow. So I need to move on. And if you have kind of intersection here, so let's talk about it. And regarding queries, so you have the new type of queries, these string queries which are forever, so probably with Kafka technology. Feel free to optimize them. You'll be very happy about it. And probably you still have some questions. I read it also.
Okay, let's finish. And we still have a few minutes for discussion questions.
How to start? This could be. This is that was one of many possible implementations of data mesh. You could always implement it as web services. Web services, right? And use this encapsulates data inside the system, and the service provides just what you want. And do you see any disadvantages of web services in this context of data mesh?
The main disadvantage here is performance. So actually, the idea of Kafka, nobody wants to have Kafka just by the rule because it's very complicated system to operate. But actually, it's unbeatable in terms of benchmark. So if you need to process a lot of messages with the high rate in the like minimum possible time, then just intensity.
First one is, so about the data contracts, are they simply the schema registry? Or can you elaborate more? Because as I understood, the schema registry is, so the producer puts the schema in the registry and then sends the necessary number of the schema. Then what is the difference between the schema registry and the data contracts here? So if they are not the same. And the second question is, I still want to understand in the end how we are, for example, every domain is emitting these events about what is happening. And then does every event has to accumulate all these events and build another table from the other domain? So for example, to join two tables, or what are we doing with all these messages in the other domain?
Okay, so the first question, the schema registry is actually implementation of the server where you can store data contracts, and this is somehow default, very powerful product of the company. You can do it also in other way. So, for example, you might put your schemas into the artifact, just have this version here, just label it, somehow put it into the repository, label the repository on server, and distribute it to producers and consumers. And they have the contract here. It can be Arbor again, so Arbor is not related to schema registry, so may just distribute the schemas in some other way. But the problem is that in operation environment, when you receive all these messages from different topics, sometimes you need to see what's inside. And if these schemas are only on producer and consumers, and you don't have central server, it's not very easy how to do. So it's kind of painful operational problem. And regarding the second question is, it's up to consumer, of course, what to do with the data. Typically, the data is saved in some kind of database. You may have some kind of streaming services before arriving to the consumer, so perform these aggregations and the joins probably. So you aggregate events from different domains, produce the results, and then consumer typically grabs the results and stores somewhere.
So with the data mesh, there is no central data warehouse.
Yes, it's very decentralized.
I have a related question because there are different places where data integration can be done. Probably small part inside the domain before sending things to Kafka or other technologies for diffusion finally. But the final work of integrating things from different domains is done consumer after consuming the data. So it can be that several consumers are doing the same work, integrating data from some subset of the producers. So how is articulate? How can this architecture evolve in this? I mean, if there are new requirements that involve new usages of data, how to avoid redoing things that are done and customers and so on. Is it possible to push somewhere in the middle or?
Oh, with this paradigm, so we can have some kind of distributed transformation. So you might have aggregation services producing results from, so you have aggregation, but you present the results which is available to different consumers. But the key point here is that we cannot do it without tools, and this is what self-service platform is supposed to handle. So we are expecting some kind of somehow breakthrough in this direction, so that we can easily find the products which are available. And this is actually the key point. If you don't know what is happening in your microservices, then how you can avoid these duplicates and how you can improve reuse.
Jump here. There is no data integration. That's the point. The point of microservices is exactly that each team is independent. So if you put, please put the slide with the one before, with the research issues. When I did my PhD more than 25 years ago, we had exactly the same research issue. And this is, I mean, data warehouses were introduced for two reasons. One was operational, that is kind of solved in the cloud and the Kafka architecture, because you can scale out and make this faster. But back then, you had to separate querying with data production. And the second one was the single version of the truth. So you integrate the data into the dimension bus. Here, all the problems that you see there are exactly because you don't have any data integration, exactly as a foundation of the architecture, because the microservice architecture is exactly this. Everyone is a silo on its own, and the teams are independent. So we're, not back in the trees, back in the caves, I don't know, because exactly we are redoing the silo thing. That was the idea back then. You had tuxedos, kicks, you have this stuff instead of Kafka, but these are the same.
But in the middle way, we have the message exchange maybe, and data virtualization, have a global view of the data store. And approach like enterprise application provision, enterprise information provision, to break down the silo. I think there's an effort to break the silo, but maybe there are each keep data independently, separately as well. I don't know.
The idea of the microservice.
Excuse me, it's time for lunch.
Oh.
And let's first thank Kat once again.